This is a quick lesson on 7.3. I want you to stop the video right now if you have not checked out yet this article, an intuitive guide to exponential functions and this number e. Read this article. If you can't read, watch the video. It does a pretty good job of just explaining exactly what's going on. But let's talk a little bit about the kind of mathematical details of what we can do with e and how we can use it. First off, remember, E is like the speed limit of growth. It's the fastest something can grow, and if we have the fastest, we can scale it down. Okay, just like I believe the article uses the speed of light. You know, the fastest something can go is the speed of light. Everything is just a portion of that. Okay, so E, we can use it to model something that grows as fast as possible. We can also model it to we can use it to model something that doesn't grow quite as fast. We can scale it. First off, manipulating E. E is a number, and a lot of times you're going to be dealing with E and a variable because by itself it's not that very interesting. So we'll have e to the 6th, e to the 3rd. Remember that when you have common bases, and even though this is a number, e to the 6th, you could type into your calculator, this, remember, turns into e to the 9th. Over on this side, cancel, of course, your constants. You got 8 over 2. That's going to be 9. And then e to the 6th on top. That will take 4 with it, leaving us with 2 right there. So just kind of reviewing some exponent properties. Remember, when you have an e inside of a parenthesis, this 2 gets distributed to both things. So you end up with a 4 to the 2nd times e to the 3x all to the 2nd. This is power of power, it's multiply. So 4 squared you could turn into 16 if you like, but more importantly, you end up multiplying 3x times 2 to give you 6x. To model something, it's going to look very similar to our original exponential functions, which looks like this: y equals a times b to the x. And b controlled growth. Well, e isn't going to change. So the way that we control growth this time is with this r value, growth versus decay. So if r is greater than 0, right here, if r is greater than 0, we are looking at growth. If r is less than 0, we're looking at decay. Basically negative. If it's a negative number, we're looking at decay. Kind of more intuitive than the 0 to 1 for the b values. Simple graph will show you pretty obviously whether it's growth or decay. One of the applications that we talk about early in math is compound interest. It's exponential, and one of the things that the article goes into is, what if we could continuously compound? What's the fastest way we could make money? If that fraction of a fraction of a fraction of a penny could start making me money, what could I get? And this is that equation. P again is principal. How much money you put in. E, of course, is just that number. So, E. R is your interest rate. And T is your time, whatever that time cycle might be. And there's not going to be an n here because it's infinite. So let's look at an example how we can use this. So pretty kind of a made-up situation here. You're not going to get infinite compounding interest, but it helps us start to use E. Deposit $2,200 into an account that pays 3% annual interest. After 15 years, you withdraw the money. So let's compare these two things: compound quarterly versus continuously. So quarterly, I'll remind you of the formula here. You've got your principal times 1 plus your rate, which is 0.03, over the n value, which is quarterly, all to the n times how many years, which is 15. Conversely, if we do this infinitely many times, you'll recognize actually that this would become almost infinite, and this would become infinite. Kind of looks like the mathematical definition of E. Well, anyways, we've got E to the rate, which is 0.03, which makes it growth. Now, not a very big growth, but growth, and we're going to multiply by 15. Type those into your calculator and you'll get your values. I just want to show you quickly where E is on these graphing calculators. There's kind of two places that you'll find it. One is going to be a little bit more useful. The first is over here, the division symbol has an E. You can push second to the E. But as I said before, most of the time you're going to be using an exponent. So we're going to use this ln button, natural log. Second E to the X will automatically set up a exponent for you. So one application of E, again, it doesn't make you a millionaire. You can see that it's 3,444 versus 3,450, but a slight difference by compounding it continuously. You're going to see E modified a lot. Here's an example of a situation, not really exponential growth, exponential decay, but something that you can use E for to model the growth of a shark. So it's got a couple of components to it here. The length of the shark is going to be dependent upon its age, but as we know, things don't grow forever. So we've got kind of this number 337 out front, and then the rest of it is a function of its age, t, which is its age in years. And so basically, you can think of this as t gets bigger and bigger. As t goes up, this thing right here is going to go down, as in it's closer and closer approaching 337. I want you to try to graph this, see what you can do with this using the E function. I'm going to jump into this question and show you on Desmos how we can use E to model something. So here we've got a population of a town. As we know, population often grows exponentially. Not always, but in most cases, you know, undisturbed. We've got a year 1980, which we are going to use as our base year right here. We have data all the way up to 89. We're going to use Desmos to try to fit this data. We're going to figure out what the population would be in 95, and then when it would hit 300 or 300,000 according to the data. So I've already got it loaded into Desmos. Here it is. I've got a nice window that will fit my data, and it does look exponential. Could we fit a linear regression to this? Probably, but we're going to use exponential. Let me show you again how to do that. First off, once your data is in, you've got to have Y1. You use the tilde button, and then I'm going to use A as my kind of beginning piece there, my starting value, and then I've got E. Go back to my functions here, to the, and I'm going to use R as my rate, and I'll go with X1 for my value, and there it is. So nice smooth green curve. If we look closely at this function, here it is. Could have probably guessed really close to 100 as a starting value. Our growth rate positive, though not very big, 0.08, maybe arguing that we have an 8% growth per year. So let's just write that down. Y equals 99 points. Let's just take a look at that. 99.9192 times e to the 0.08x. What was the population in 95? That would be an x equals 15. That's 15 years after 1980. So we'll go over and graph x equals 15. We've got a vertical line. Find the intersection by simply tapping on it. Looks like there would be 332,000 people. So 332,000. Okay, roughly. When did the population, or when will the population hit 300,000? So we'll jump back over, graph y equals 3,000, or 300, I should say. And there it happened 13 years after 1980. We call that 1993. Roughly.